You're surrounded by data and numbers every single day. But how do you know what's real? Today, we're going to pull back the curtain on statistics to find what we're calling an honest answer. We're talking about the real story behind the numbers that kind of shape our world.
So let's be real. We've all seen a slide like this, right? It's just this wall of complicated formulas, and then somewhere in the middle, it just says, then a miracle occurs. It can feel like science is some kind of magic trick that you're just not in on.
Well, that's exactly what we're going to do here. The whole point of this explainer is to pull back that curtain to show you what's happening during the miracle. No magic, I promise, just clear, logical steps. And hey, let's be super clear about the goal here. This is not about turning you into a statistician overnight. Nope. It's about empowering you so you can be an intelligent consumer of science. So the next time you see a news report or read a study, you'll actually have the tools to know what the data is really trying to tell you.
Okay, so let's dive right in by asking the big question, why should we even care about any of this stuff? How does it pop up in our actual day-to-day lives? The thing is, statistics are, well, they're everywhere. When your map app estimates your arrival time, that's statistics, predicting an outcome based on tons of data. And when you're in a casino, the house always has an edge, and that edge is calculated with, you guessed it, ruthless statistical precision. At its core, statistics is the language we use to make decisions when we don't have all the facts.
To really get how it all works, we need to understand two key concepts, and we're going to explore them by going on a simple, pretty practical quest together. So imagine this. Our job is to find the average height of every single student at a university. This one simple question is going to guide our whole journey right into the heart of what statistical thinking is all about. First up, we've got this idea of a population. Now, this is the entire group we're interested in. So for our little quest, the population is every single student enrolled at that university, the whole shebang. Now, just look at this. Could we realistically get every single one of those thousands of students to line up and let us measure them? Probably not. It's usually way too impractical, too expensive, or sometimes just flat out impossible to get data from an entire population. So we do something much, much smarter. We take a sample. A sample is really just a smaller, more manageable group that we pull from that larger population. And the really crucial part? This smaller group has to be a good representation of the bigger one. That's key. So instead of trying to measure every single person in that whole stadium, we might just measure the heights of students in, say, this one section. This is our sample, and from this one little group, we're going to try to figure out our answer. All right, so we've got our sample, we've measured all their heights. The next step feels pretty simple, right? But this is where things start to get a little bit tricky. So we calculate the average, or the mean, of all the heights in our sample. Let's say we do the math and we get a single number, 166 centimeters. In statistics, this is called a point estimate. It's basically our single best guess for the true average of the whole population. But here's the all-important question. Can we confidently just walk away and declare that the average height of all students at the university is exactly 166 centimeters? I mean, how much can we really trust this one number? See, here's the problem. What if we had picked a different section of that stadium, a totally different sample? We would have gotten a slightly different average, maybe 165 centimeters, maybe 167. Our single number of 166 is probably close to the true population average, but it's almost certainly not exactly right. It gives us this false sense of confidence because it completely hides all of our uncertainty. So to build a more honest answer, we need a way to show our uncertainty. And the tool that statisticians came up with for this is, well, it's just beautiful in its logic. It's called a confidence interval. To build that interval, we first have to understand that data, like our student heights, is usually spread out in a pretty predictable way. You've probably seen this classic bell curve before, the normal distribution. It just shows that most people are somewhere near the average height, and fewer people are way out at the extremes, either super tall or super short. So how do we measure how wide or how narrow that bell curve is? Well, we use a number called the standard deviation. You can just think of it as a measure of the average distance each student's height is from the middle, from the mean. A small standard deviation means everyone's kind of clustered together. A large one means the heights are much more spread out. And this is where it all clicks into place. By using the mean and the standard deviation from our sample, we can finally move away from that single, probably wrong guess. We can build an honest interval. So instead of just saying the average is 166, we can now say something much more powerful, like we are confident the true average is somewhere between, say, 161 and 171 centimeters. See? This range, that is our honest answer, because it actually captures our uncertainty.
Okay, but hang on. This brings us to one of the most misunderstood ideas in all of statistics. You always hear that phrase, right? We are 95% confident. What on earth does that actually mean? I promise you, it is not what most people think. So here it is, the classic misconception. Does our interval, the one from 161 to 171 centimeters, have a 95% probability of containing the true, unknown average height of all the students? I mean, it sounds right, doesn't it? The answer, and this might surprise you, is no. That is not what it means. Just let that sink in for a second. Think about it. The true average height for the entire university, well, that's just one specific fixed number. It's like an anchor. It doesn't move. So our interval that we calculated either contains that true number or it doesn't. The probability is either 100% or 0%. We just don't know which one. So where does the 95% come from?
Okay, here's the real meaning. The 95% confidence isn't about our one specific interval. It's about the method we use to get it. It means that if we were to do this whole thing over and over again, like 100 times, taking 100 different samples and creating 100 different intervals, we would expect that our method would succeed in capturing the true average about 95 of those times. The confidence is in the process, not in any single result. So we've gone from a fragile single guess to a much more robust interval. But how do scientists actually use these tools to make discoveries? Because often, it's not about just one group. It's about comparing two. For example, is the average height of engineering students actually different from arts students? To answer that, scientists often calculate something called a p-value. You can think of it like a probability score. It tells you the odds that the difference you're seeing is just due to random luck. A really small p-value suggests a statistically significant finding. But this little number has actually become pretty controversial, partly because a significant result isn't always a meaningful one in the real world, and that nuance is right at the heart of the replication crisis in science today. So there you have it. We've taken a journey from a simple, fragile guess to a much more honest answer. We've seen that a single number can be really misleading, but a range can tell a much truer story. So the next time you see a statistic, ask yourself, what uncertainty is being hidden here? Because demanding the honest answer, the one that admits what it doesn't know, that's not just about understanding science, it's about understanding the world.